Welcome back. Next I want to explain to you some certain effects of these summaries that IFDS is actually generating. And in particular, these summaries have some very nice properties compared to the summaries that we saw in the case of Vasco. And that is because these IFDS-based summaries, they tend to be more reusable. So typically they are reusable across a larger number of calling contexts. And that's very nice, right? Because the higher the number of contexts is in which you can reuse a certain pre-computed summary, of course, the less computation you need to do overall. And that's really the main advantage that IFDS has over Vasco. So let's assume that, again, we have such a summary function here that has been computed for a procedure, right? So here, this is basically marking the beginning of some procedure, and it can be arbitrarily large. But we know that at the end of the procedure, let's say, if A was tainted in the beginning, then B will be tainted afterwards. Or more general, you will see that this summary is actually saying this here. So it's saying in any calling context, it doesn't matter which one in particular, but any calling context in which A holds before the call. In this calling context, it's true that B holds actually after the call. Okay, so again, we have some implicit quantification over calling contexts here by this. You can read this as a rule, right? So this is basically the top half of the rule. So this is saying to which contexts the summary applies. And then this is saying what the effect is on this context. And like I also said, 0 doesn't really need to be represented in a summary because it always holds, right? So in practice, we wouldn't actually store this. So what's important now about these IFDS-based summaries is that these summaries, like you see it here, they're actually point-wise summaries. So this here, the summary is really a summary regarding A, right? So this comprises of this node here and all the edges that go out of A, and all the target nodes. But then you can have other point-wise summaries for other inputs, such as B and maybe even some other values. And these summaries can then also be reused partially. So that means if you have a context, for instance, that taints A, then it will actually look at the summary edges that go out of A and only those. It doesn't matter what the summary edges for B are. The other way around, if you have a context that taints B, then only this part of the summary matters, only the edges that go out of B matter. And that is exactly because they have a distributive problem. Because of distributivity, you know by definition that these input values, they can be treated independently. If you remember this graph that I showed you at the very beginning, where we were sort of constructing a summary function out of individual distributive flow functions, that's exactly where this pays off. Now, to show you this in an example, you will see that these summaries, they can really be reapplied in every different calling context. And then it will look as such. So let's assume we have such a main method here that has a call side here. And initially, this main method is tainting X. Okay. And then we have such a call flow function that maps X to A. And by looking at this procedure summary, we simply know ahead of time that A is being mapped to B by this callee here. Okay. And now just for the sake of the example, let's assume that now the return statement maps B to Y here. So after the statement, just through this call statement, we have the situation that now Y is tainted and X is no longer tainted. Okay. And then we call the same procedure again, right? So now the situation has changed. Previously, X was reachable. This time, Y is reachable. And now we will see that when we assume that Y is now assigned to B, so this is now a tainted parameter. By looking at the summary, we will see that we have a summary for B, right? So the node B here It's part of the summary, so a summary for B has been computed, but the summary is telling us that there's actually no outgoing edge of B, right? So that means B is to be killed, okay? And no return flow therefore needs to be computed. So what you will see here is we have the same summary as before, right? So the summary I did not update. It's the same you saw for the first call site, but it has a very different effect, right? So at the first call site, because A was tainted, we were propagating a taint to Y. But at the second call site, because now another input parameter is tainted, just by looking at what happens to this parameter according to the summary, we know that now we have a different effect. So now nothing is being propagated. In fact, B is killed, right? So you have the same summary function, but a different effect, okay? And that's really a nice property, right? So these, like I said, these summaries, they can be read pointwise, right? So effectively, this is a summary for A, and this here itself is a summary for B, and you can use them individually. That's very different from what we had in Vasco, right? So remember in Vasco, we had this example here where basically we had two different calling contexts, and in the one calling context, this parameter I up here, it was assigned 2, and in the other 3. But actually that didn't matter at all to the summary, right? Because, well, I is really being printed here only, and it has no effect on whatever is being computed. But nonetheless, we had this recomputation here, right? And in IFDS, you can omit something like that, because basically you can have a summary for H, and you can have a summary for I, and whenever I changes, you need nothing to recompute about H, right? And the other way around. So you can really do this individually. And in fact, there are even approaches such as sparse IFDS, which was published recently, that take this to an extreme. There you really only consider in any callee evaluation exactly these statements that are relevant to re-evaluating a particular given single parameter. Something that I still want to briefly explain is this requirement for a finiteness of the domain in IFDS. So like I said earlier, so a finite domain is really a requirement. So if you have an infinite domain, IFDS is really not applicable because you basically can get non-termination. But even if you have a finite domain, a recommendation of mine would be to keep your domain rather small. And let's see why that is. So let's assume we want to encode into IFDS the problem of linear constant propagation. And I've explained this before. So if you have a general constant propagation, then here in such statements, you could have dependencies on two variables, right? So you could have something like v plus u, for instance. But if you have dependencies only on a single variable, then we're talking about so-called linear constant propagation. And linear constant propagation is a distributive problem because here you only have a one-on-one dependency. And one can show that this is then distributive. So this is a problem that you can encode in IFDS. So it's possible in principle, except for this finiteness issue. And that you will see when you actually look at how this would need to be encoded. So opposed to a taint analysis, we now not only need to store the information that V or R is tainted, but we actually need to associate with each of these variables a concrete, in this case, integer value, okay? And that means that our data flow domain will look like this, right? So we will have pairs or mappings from variables to numbers, right? And this is then also reflected in our exploded supergraph nodes. So now we have these compound nodes that represent a combination of a numeric value with a variable, right? So if this node is reachable in the graph, it's now telling us that V can have value 1 at this particular program statement or this program location, right? And so if you now then have such a summary here for such a statement, for instance, Um, and so let's assume, for instance, that we have a procedure that contains this body here, right? This statement as a procedure body. Then this could be a procedure summary, and it would read as follows. So this would say, in any context in which v is 1 before the call, it is true that r is 2 after the call, right? Because we have this edge here. So, like I said, you can encode it this way, right? But the problem is now that this is a rather large domain, right? So we can have, the number of natural numbers is infinite, right? So in essence, you can have an arbitrary number of these kinds of tuples or pairs. And this actually can become a problem when you want to summarize things such as this increment function here. So let's take a look at this program. It's starting off by incrementing 0, which is then assigned to x, but then it's incrementing that value, and it's incrementing again and again, okay? So at the first call, we will be creating a summary that looks like this. We would be saying, okay, given the first calling context, we now know that x has the value 0, and therefore also v will get the value 0. And looking at this procedure and analyzing it, we have now discovered that if v is 0 at the beginning of the procedure, then r is 1 at the end of the procedure. So we would have such an edge. Okay? But the problem is now that at the second call, this one here, you would have to create a new summary. We would have to reanalyze the increment procedure because none of these summaries here matches, right? We do have a summary for v0, but here, after we have processed this call flow function, we have a pair v comma 1, which is different from v comma 0, right? So we have no matching summary. We would not be able to reuse it. We would have to reanalyze that procedure. And we would again then, after reanalysis, get such a summary that's telling us, okay, if v was 1 initially, then now r is 2 after the procedure call. And this can go on and on and on, right? And now I've done this for 3 different call sites here. And you can already see that this is exploding, right? But if I had had a loop around this, that would have led to repeated recomputation of this increment method, I might even get non-termination, right? Because then I would basically create this over and over again. I would be creating new summaries. And then, yeah, what can you do, right? I mean, you can artificially bound your domain. You can basically do a widening. We have seen that, but it's all pretty nasty, right? And so IFDS is really useful when you have reasonably small domains, typically domains that encode static information really about your program, such as variable names, for instance, and maybe a bit more limited information. But as soon as you have runtime values, such as these numeric values here, or maybe also some larger sets of object pointers or so, that can become a bit problematic because then you have very large domains. And with large domains, you tend to get large sets of summaries. And then, of course, if you have such large sets of summaries, what does it mean, right? It means that the likelihood that you are reusing any of these summaries is actually very low, right? So you end up creating lots of summaries, but maybe never or almost never using them. And then what's the point of creating a summary in the first place, right? There is no point. That's really quite pointless, literally. And so that doesn't really make any sense. And so therefore you should strive for a rather small domain when you're using IFDS, not just finite, but small. And to sort of bring this back to what I originally explained about Vasco, I want to show you this slide again. So when I was talking about the functional approach and then Vasco, I was also talking about the fact that in the functional approach, the challenge is actually to create sort of symbolic summaries, right? Or summary functions that can be symbolically represented. And another term for this is a so-called intensional function definition. That's opposed to extensional function definitions. So an extensional function definition looks like the one we have actually seen for Vasco, and it's actually also similar to the one that we have seen in IFDS, right? So in Vasco, we really had this situation where we were mapping really a concrete input environment to a concrete output environment. And then if anything in the input environment changed, we would have to reanalyze the procedure and we would create a new input environment and compute how that is being turned into the output environment, right? And in general, you can denote, for instance, also an increment function such as this, right? So an increment function tells you if you give me 0 as an input, I give you 1 as an output. If you give me 1 as an input, I give you 2 as an output. That's a so-called extensional definition, and Vasco has exactly that. Now, an intensional definition, it abstracts away the concrete input values through these variables, like you see here. So this is saying, no matter what the input is, let's just call it x, right? So lambda x. X is being mapped onto x plus 1, right? And so what you get here, it's really a very concise definition, right? Because it has this abstraction. It actually works for infinite domains because this abstracts over an infinite number of concrete inputs. But it requires such a closed form, right? So you can only denote such a function intentionally if you can find a closed form for that denotation, right? That's a requirement. And so far, we haven't really seen how that works, right? I told you that we want to get there with distributive flow functions, but we haven't really seen that yet because in Vasco and also to a large extent in IFDS, we rather have such mappings here, right? So they talk about concrete input values and map these to concrete output values. And this then only works for a finite domain, right? Because otherwise you can immediately see you get an infinite representation here. But the advantage here is that this is universally applicable, right? So you can take any arbitrarily complex input here and you can map it to any arbitrarily complex output because you don't really need to describe the function otherwise, right? You just need to denote that mapping, and there's no symbolic or intentional definition of that function, right? And Vasco and IFDS, they really fall into this category, so they talk about these extensional definitions, whereas the advantage of IFDS over Vasco is really here that basically these input mappings, you can deconstruct them, right? So you can really talk about input mappings for individual variables or individual data flow objects that you have in your abstract domain. Whereas in Vasco, you always need to look at the concrete, complete input mapping, right? And so in Vasco, the likelihood that you actually have a reusable summary at a given call site is therefore lower because the summaries, they are only reusable if they are completely reusable. And in IFDS, you can reuse them, like I showed, even just if they are reusable for the data flow fact that really matters to you at the moment. Now, next week, we will be talking about another approach, which is called IDE, Interprocedural Distributive Environments. And that is actually an extension of IFDS that gives you this here. So for the first time, this will be an approach that actually computes intentional function definitions. And therefore, it can also deal with infinite domains. And because it is distributive, right, so that's the D in IDE, because it is distributive, there's actually a principled approach in which you can construct such a closed form. So it is an approach for which we have this nice representation here, but we also know how to construct it. And that brings me also to my recap about this week's lecture. So I was talking about IFDS and how it is restricted to problems that use set union as merge operator and flow functions that are distributive over this operator. Okay. I actually didn't talk too much about why we use set union as a merge operator. So maybe let's spend another minute on this. Why does it have to be set union? Well, if you think about it, in IFDS, like I said, the program analysis problem, it's transferred to a problem, or it's reduced to a problem of graph reachability, right? And if you think about graph reachability, when is a given node reachable in a graph? Well, it's reachable if it is reachable across any or along any path that leads to this node, right? So it's really an existential quantification. You are saying as long as there exists any path that leads to this node, the node is reachable. And that's exactly the union semantics that you get here, right? So it's really by the construction of that graph that you really get set union here, and that you are restricted to using set union. And if you wanted to use another merge operator, you could not simply use graph reachability because, yeah, it simply wouldn't fit that problem anymore. So, but in those cases where you have this, right, so where you can use union as a merge operator and where the flow functions are distributive over the merge operator, you do get an efficient and fully precise context-sensitive solution, right? And IFDS, if you have a reasonably small domain, it's really very efficient. So it's cubic in the size of the domain. And so if you have, and that's the worst case actually. So if you have a relatively small domain, then you will also get an efficient solution. If you have a large domain, then, like I said, it's not suitable, but IDE can actually help with that, as I will explain next. And the principle of IFDS is based on these summaries that are reusable on the level of individual domain values, like I showed you. And that's really the important defining difference to Vasco, because here you can really reuse summaries on the level of these individual values, which with Vasco you cannot. That concludes my presentation for this week. Thank you very much.